Hi, and welcome back to Batty.com. Today we're going to talk about an advanced subject, and that is some of the signals that are present inside the digital cluster. This video will probably be more of interest to electronics technicians and folks with an oscilloscope or a graphing multimeter. All right, let's get started. Okay, so the first thing we will do, we'll clip our ground lead onto a known good electrical ground, like this power supply. And again, we're clipping onto the negative side of that capacitor. Today we're going to talk about signals. Signals are voltages that change over time. Here we see a typical sine wave. It's being made by my function generator. In just a second, we'll look at some of the signals that are generated by the digital cluster. Our scope is set to 2 volts per division in the vertical direction and 2 milliseconds per division in the horizontal direction. When we look at pin 6, what we see is that this is a square wave. It is approximately 4 divisions long, or 8 milliseconds long, and it's about 8 volts peak. If we use the scope for measurements, we see that it's got an 8.48 volt peak, and it is 122 hertz frequency. What this is showing us is the square wave, which drives the brightness of the LEDs. This is a pulse width modulated signal. Right now the cluster is laying down, which means for the most part the photocell is dark, and this is the way the signal looks when the photocell is dark. I'm going to stand this up, and what we see is that the brightness, as the brightness of the photocell increases, the duty cycle goes to 100%. As we darken it, the cluster will bring that duty cycle back down. Sometimes it takes a little bit to respond. Now we're at about 50% duty cycle. Now we're at a little bit less than 50% duty cycle, back where we were. Next we'll look at pin 7. This is going to be a signal called clock on the schematic diagrams. This is serving to clock information into the memory array on the LCD driver board. That memory array is nothing more than a several hundred bit long shift register, and it's this clock signal that drives that array. If we look closer at that, I'm going to zoom in a little bit. What we see is that it's a series of very short pulses. Each one is 8.5 volts in amplitude, and each one of those is 5 microseconds in length. Okay, the high portion is 5 microseconds in length. They are spaced 100 microseconds apart, and if we look at them as a group, we'll see that there are hundreds of them that correspond to the hundreds of bits of information that is being sent from the digital cluster to the LCD driver board memory array. If we zoom out further, we see that those groups are being sent approximately every 60 milliseconds. A group is about 25 milliseconds in length, and those groups are being resent approximately every 60 milliseconds. The next thing we're going to look at is the data. The data line is pin 8 on the board connector set. And if we look at this, the data corresponds to information that is being sent from the microcontroller to the LCD memory array. If we zoom in, we see that things are not necessarily evenly spaced, and that's because each one of these bits in time, each one of these pulses or missing pulses corresponds to a 1 or a 0 in the data stream that is being sent to that memory array. If we zoom out a bit, we see that again, we're looking at about 25 milliseconds worth of data. If we zoom out even further, we see that those data packets are being resent approximately every 60 milliseconds. If we look at the final signal that is associated with the LCD shift register memory array, this is on pin 5. This is going to be called strobe or data strobe by the datasheet. This is a much harder signal to see, and the reason for that is that it is very brief and very far spaced apart. Very faintly, what I'm seeing is a pulse approximately every 60 milliseconds. This pulse occurs at the end of the data packet, and it's used to latch the data that's been received by the shift register into memory so that it can be displayed by the LCD panels. We have to zoom in quite a ways to find out what size it is. And we're looking at again a 5 microsecond pulse. And its amplitude is about 8.5 volts. If we zoom out far enough, we'll see those pulses spaced every 60 milliseconds to indicate the end of each data packet. I just want to show you that this is a working cluster. There are currently no signals being fed to it. It just has power applied. For the next test, okay, we're applying a sine wave of 40 Hertz to our speedometer signal. And what we see is that the speedometer indicates approximately 35 miles an hour, 36 miles an hour. The next signal we'll look at is here. What we see is a square wave. The square wave measures 50 milliseconds in length, and the amplitude is between 5 and 5.5 divisions at 2 volts per division, so it's about 11 volts in amplitude. If we go and do our measurements on the scope says yes, indeed, it is a frequency of 20 Hertz and 11.1 volt peak. Our duty cycle is about 50%. I'm going to increase the frequency that we're feeding into the speedometer input. I'm going to run this up to 100 Hertz. And what we see on the output at the odometer connector is that the voltage didn't change, but the frequency did change. So we're getting a square wave output that is proportional to the speed that we're inputting into the speedometer input. As we crank the speed signal back down to 40 Hertz, we see that the frequency of that square wave gets slower. Really what's happening here is this is a stepper motor driver circuit. That odometer motor that you have is being driven by pulses that are coming out of these two pins. We look at them, they look pretty much the same, different in polarity. And if we hook that stepper motor up, we'll see this is an odometer motor, just like you have in your odometer. It sits right here. We'll see it turning very slowly. And as we increase the frequency, I'm now increasing it to 100 Hertz. The motor speeds up, it drives your odometer faster. And if we look at those signals together, here's what they look like. We see a burst of data clock signals. We see the data that it's shifting into the shift register. And at the end, we see the latch signal or the strobe signal, which causes all of that data to be sent to the memory, the outputs of the memory array, the outputs of the shift register, and displayed on the LCDs. Here we see channel 1 is the yellow trace. That is the strobe. Here we see channel 2 as the blue trace. That is our data clock, or our clock signal. And the magenta trace is number 3 and it's connected to the data line of the board connector set, pin 8. We're looking at pins 5, 7, and 8. These are the 3 signals that are necessary to drive the LCD array. There's a 4th signal that we also showed you that is on pin 6. That is the dimming signal. The duty cycle of that controls the brightness of the backlight bulbs. Here we are looking at the bottom board, and if we look, we see that pin 4, which is our 8.2 volt power supply, is connected to pin 1 on each of these ICs. If we look at pin 5 of the board connector set, we see that it's connected to pin 2 of each of these ICs. If we look at pin 5, which is our data strobe, or our strobe signal, we see that it's connected to pin 2 of each of these ICs. If we look at pin 7 of the board connector, which is our data clock, we see that it is connected to pin 40 of each of the ICs. And if we look at pin 8, which is our data signal, we can see that it is connected to pin 34. Now, it's not connected to pin 34 of every IC. And the reason for that is that these are chained in series. Pin 34 is the input. Pin 35 is the output. So when it comes out of the first IC on pin 35, it goes into the second IC at pin 34. If we look at the next pair, we'll see that the output, pin 35 of the second memory, is connected to pin 34 of the third IC, and so forth. So the data is being passed from the output of one memory IC to the input of another memory IC. A fairly common failure mode is for part of the LCDs to work, and those are typically the LCDs on the left side of the screen, like your speedometer. These ICs are extremely static sensitive, and if one of these ICs dies, it will stop outputting, so the information stops being passed from IC to IC. So what you'll see on the LCD panels is that information on the left side works, and at some point everything past a certain point on the LCD panels is simply blank. It's set to black or no data. So what we should see is on pin 34 is our data signal. We'll see our data signal again. If we look at 34, which is the input, we'll see our data signal. If we look at pin 35, we'll see our data signal. And this should continue all the way across the board. If we look at 35 and 34 on the very last IC, here's pin 35, pin 34. Seeing our data signal at the very last output, pin 34 of the very last IC in the chain, tells us that all of these ICs are working correctly. Something else that's fairly common is for bad solder joints, typically on the board connector set here, to not pass signals from the top main logic board to the bottom LCD driver board. This can happen whether the board connector is new or old. It really just depends on the quality of the solder work done. The way we check those necessary signals are at, again, we're looking at pin 1. We should see a constant 8.2 volts. On pin 2, we should see our strobe signal. It's tough to see, but I am seeing it. And we'll check for that strobe signal on multiple ICs just to make sure it's making it to everything. There are no breaks in the traces on the board. The next thing we'll look at is pin 40. Make sure our data clock signal is making it to the bottom LCD driver board. In this case it is. We're looking at pin 40 on all of those ICs, and they all look good. If we're having backlight issues, is look to make sure the PWM dimming signal is making it from pin 6, which is right here, through to the bottom board. In our case it is. It shows as high, and then when we cover the photo cell very slowly, what we'll see is the duty cycle change. Very slowly what we'll see is the bulbs dim. We'll see relatively dimmer bulbs. And we'll see that our duty cycle has changed from 100% down to about 40%. When I allow the light to reach that photo cell, what we see is that the bulbs brighten up and the duty cycle approaches 100% on pin 6. If that's not working, let's look at the signal present at the base of that transistor. And again, when we cover the photocell, what we should see is that it slowly reduces from 12 volts to a duty cycle that is closer to 50%. I'm going to show you, I'm going to zoom up and show you that. What we see is our duty cycle is about 40 to 50% when the bulbs are dim. And it changes to 100% when the bulbs are bright. Okay, the final signal that I'm going to talk about is the clock signal that's being presented to the microcontroller. This is being measured across the crystal, but it's also present across pins 2 and 3 of the microcontroller. And if we look at our screen, we have a signal that is approximately 4 megahertz in frequency. It's about 2.5 volts peak. If we look at the other side of the crystal, we see something very similar to that. We'll see the same thing at pins 2 and 3 of the microcontroller. If the clock drive signal is not present, that might be why code is not executing on the computer. And you might check for broken terminals on the crystal. It's fairly easy to break the crystal away from the motherboard when you're working with it. The next signal we're going to look at is pin 6 of the microcontroller, and pin 6 of the microcontroller is the reset line. Just want to show you what I'm measuring here. Pin 6 of the microcontroller is the reset line. It is critical that for the microcontroller to run, the signal needs to remain high. If what you saw was a square wave that was approximately 1/2 to 2 hertz, that is the watchdog circuitry recognizing that the recognizing that code is not running and it's trying to reset the microcontroller. In that case, you'll have to do much more extensive diagnosis to figure out what's happening. Thank you very much for watching. I hope this helps you to troubleshoot the signals that are associated with the digital cluster. We'll see you back here next time on Crazy Uncle Burton. As always, you can go to batee.com, that's BATEE.com, for parts, schematics, wiring diagrams, and help troubleshooting problems with your cluster. Thank you very much for your support.